One of the primary needs of people, and more generally of human communities, is to have access to clean, safe water in sufficient quantities for all personal and collective needs, including those related to productive and recreational activities. The purpose of water supply infrastructures is to meet these needs in an optimal and sustainable way. To achieve this result, it is necessary for different engineering works to be integrated into complex systems for the collection, storage, transport, treatment, and distribution of available water resources. These systems must be able to continuously adapt to changes caused not only by natural cycles, but also by the combination of individual choices made by many people and of the operational cycles of different activities, always ensuring optimal conditions of usability and safety. In recent years, water supply infrastructures have been finding it increasingly difficult to achieve a sustainable balance between demands and available resources, with a growing frequency of water crisis situations, even in areas that were once not considered at risk. On one hand, the decrease in resources can be attributed partly to the effects of climate change, but also partly to widespread environmental pollution, which is increasingly imposing technical and economic constraints on the use of many water bodies. On the other hand, the ever-increasing concentration of people and activities in increasingly dense urban areas has, in recent decades, led to a growth in water demands that is faster than the ability to upgrade water transport, storage, and distribution infrastructures. This critical and rapidly evolving situation makes traditional strategies, which are mainly based on seeking new water resources and building new infrastructures, no longer adequate to meet these challenges. There is therefore an increasingly urgent need to a transition toward more efficient, sustainable, and resilient water systems through strategies that prioritize adapting to changes rather than fighting against current trends. These strategies are mainly based on 5 pillars: greater protection of natural water resources, prevention of overexploitation and pollution risks, reduction of water losses, limiting water waste, differentiating types of water resources according to their use, and promoting reuse. To achieve this transition, it is already possible today to use the tools provided by the digital revolution, as well as to experiment with new solutions. In particular, on one hand, there is the possibility of creating networks of sensors and autonomous valves, interconnected with each other, which allow for real-time control and regulation of the various subsystems, also thanks to computerized digital models, the so-called digital twins. The goal is both to promptly identify anomalies, such as water leaks and functional irregularities, and to increase the infrastructure's ability to efficiently and dynamically adapt to changing operating conditions, even in the event of emergencies, while minimizing water waste and energy consumption. On the other hand, there is the possibility of using non-conventional water resources to supplement those already available today. These are waters already present in urban areas which, although not of high quality, can still be easily used for non-potable purposes, possibly after some simple treatment. This type of resources includes rainwater, shallow groundwater, graywater, treated wastewater, and wastewater from technical and industrial plants. Their widespread use and reuse could meet up to 50% of residential needs, increasing the efficiency, sustainability, and resilience of water supply systems. Moreover, the use of these unconventional resources would help preserve valuable and vulnerable natural resources, save energy, and reduce pollution in water bodies.